Okay, nice. So today we have our last tutorial question. So it talks about the stress transformation or how to get the principal stresses. So our first question is a very simple one, and it asks us to find the principal stresses for the following point or element. As you can see, for this element, we have some stresses given to us. This is stresses, 200 MPa, and we have as well this is stresses, which is 350 MPa. As you can see, this stress is type of normal stress, and this stress is shear stress. So we have elements subjected to some normal stresses and some shear stresses, and what we want to find is the principal stresses due to sigma, the normal stress, and tau, shear stress. Okay, this is our idea. So I will just now open and Paint to okay. So we have question number 1. We have a small element under stresses. So this is the stresses given to us. Again, this was 350 MPa, and this was 200 MPa. And the requirement is please find the principal stresses on this element. The principal stresses has the name sigma 1 and sigma 2, or sigma max and sigma minimum. Okay, so principal stresses are sigma 1, sigma 2, or sigma max, sigma minimum. What is the formula for sigma 1, 2, or sigma max, sigma minimum? So sigma 1, 2 equal to sigma x plus sigma y over 2 plus or minus root just a second to show you the we'll show you first the formula. So if you look to the formula here, so this is our formula for principal stresses. As you can see, sigma 1, sigma 2 equal to sigma x, sigma y. So there is a problem here. So this is sigma y, not sigma x. So please change it on your, if you download the file from the Learn Online website. So this is our formula. So sigma x plus sigma y over 2 plus or minus sigma x minus sigma y over 2 all squared plus tau x y squared. Okay. So if we return back to the Paint file here, so okay, Jacob, I will just continue, but I am talking about the general formula first, and I will let you know why it is 0. Okay. So now the formula is again sigma 1, 2 is equal to sigma x plus sigma y over 2 plus or minus, what was it? Sigma x minus sigma y all over 2 all squared plus tau xy squared. So this is our general formula for principal stresses. As you can see, sigma x and sigma y are normal stresses. And tau xy, what is tau xy? Tau xy is shear stresses or shear stress, sorry. Okay, so we have sigma x, sigma y normal stresses. Tau xy is shear stress. For our example here, what is given to us? Given to us this small element, we have, this is the normal stresses we have, 200 MPa. And we have some shear stresses or type of stresses here, 350 MPa. What this stress is? This stress is stress normal to the element, so it is normal stress. Okay, again, what is this stress is? This stress is normal stress because it is normal to the element sides. Okay, this stress, if this our axis, x and y. This is stress in x direction or in y direction? In y direction. So this is sigma y. So in this example, we have sigma y equal to 200 MPa. Okay, but tension or compression, this we need to know this as well. Tension or compression. If we go back to the example again, just quickly. The arrow here is going into the element or out of the element? Into the element. So it is compression or tension? Should be compression. Because here, if you look here, so the arrows getting into the member or the element, so it is compression. If it is compression, so the sign for this stress is negative. So negative indicates compressive stress. Okay, so sigma y is negative 200. Okay, now in x direction here, in x direction, is there any stress in x direction? Jacob, do we have any stress in x direction according to the given information? What do you think? What do you think, guys? Do we have any sigma x here? Do we have sigma x or we don't have? Okay. from the information given to us, we don't have any sigma x, so sigma x is 0 because there is no stress in x direction. Okay, what other stresses we can have? Shear stress. If we look here, what we have here, these arrows, we have 350 MPa. This stresses is parallel to the element sides. So this stresses is shear. So we have tau xy is 350 MPa. So we have shear stress in this problem equal to 350 MPa. For the shear stress, it doesn't matter positive or negative for us. So the sign is not important for us in the shear stress. So it doesn't matter. So take it positive, will not affect our answer. So now for our formula again, sigma 1, 2 equal to sigma x plus sigma y all over 2 plus or minus root sigma x minus sigma y all squared over 2 all squared plus tau xy all squared. Okay, so 1 will be with the positive, 2 will be with the negative. This is how to deal with the equation. So we have now sigma 1, 2 will be equal to 0 minus 200 over 2 plus or minus root 0 minus 350, sorry, 200 over 2 all squared plus 350 squared. Because tau is squared, so it doesn't matter positive or negative, it will be positive. That's why the sign is not very important to us here. So if we substitute here, we will have sigma 1, 2 equal to negative 100 plus or minus root 100 square, negative 100 square plus 350 square. Okay. So we will have sigma 1, 2 equal to negative 100 plus or minus we have 100 square plus 350 square to 100 square plus 350 square root 2. So we have 100 squared plus 350 square under root. So it will be plus or minus 364. So now we have Now we have sigma 1 equal to negative 100 plus 364, so it will be plus 264 MBA, and we will have sigma 2 equal to negative 100 negative 364, so it will be negative 464 MBA. So we have here sigma 1 and sigma 2. So the principal stresses for this element are positive 264 MBA and negative 464 MBA. Okay. Do you have any question regarding this problem? So this problem is straightforward, just to know what is the stresses applied and how to use the formula. Do you have any question, guys? This is the problem we have done. Do you have any question, guys, for this one? No? I'm recording. So our second problem today is simple beam with applied load of 12 kilonewton at 3 meter from support B, 4 meter from support C, and we need to, the cross section of this beam is a rectangular section, 200 by 300 millimeter, and the requirement is to find the principal stresses, sigma 1 and sigma 2 at point A, which is 2 meter from support B and 75 millimeter from the bottom. Okay. For this example, we don't have, if we return back to our formula, so our formula is sigma 1, 2 equal to sigma x plus sigma y over 2 plus or minus sigma x minus sigma y all squared over 2 all squared plus tau xy squared. So first of all, we need to find what is sigma x and what is sigma y, and also what is tau xy is. How to find these stresses? To find these stresses, first of all, we need to, so our first step is to calculate the shear force and bending moment. So SF and bending moment BM at point A. To find or to calculate the shear stress at point A, what we need to do is to, first of all, this is our beam, 12 kilonewton, 3 meter, 4 meter. So we need to first, step number 1 under this will be calculate the reactions. So our first step is to calculate the reaction. How many reactions we have here? So if this support B, this support C, so we have YB and XC and YC. So if we apply summation X equal to 0, so XC equal to 0, summation MB equal to 0, so we have YC times 7 minus 12 times 3 equal to 0, so YC will be 5.1428 kilonewton. Apply summation y equal to 0, so we have YB plus 5.1428 minus 12 equal to 0, so YB equal to 6.857 kilonewton. So the reaction here equal to 6.857 kilonewton. The reaction here is 5.1428 kilonewton. What is the next step is under this will be draw or calculate shear force and bending moment at point A. Okay, where is point A? Point A is here. So point A is 2 meters from here. So if we draw the shear force diagram first to make it easier. Okay, so this is again our problem and this point A. So this is 2 meters. So if we draw the shear force diagram and the bending moment diagram here. So we will just add the reaction again. This was 6.857 kilonewton and this was 5.14 kilonewton. So this is the data. So I will draw the shear force diagram first. So how to draw the shear force diagram here? If we return back to our previous tutorials, this will be our first section, section number 2, section number 3, section number 4. So this is our sections. So here, the shear at section 1 will be this 6.857 and we'll go straight because no forces, 6.587. Then we go back, we drop 12. So we will go to 5.14 and then no load, so straight. Then this will close the diagram. So this value is 5.14. This shear is negative, this shear is positive. The moment diagram will be, this is our data, bending moment diagram. So as you know, the moment at section 1 will be 0. The moment at section 4 will be 0. The moment at section 2 and 3, so M2 or 3 will be 6.857 times the distance, which is 3 meters. This will give us moment of 20.57 kilonewton meter. So the moment here is 20.57. There is no uniform load, so the moment will be straight line. And this is our bending moment diagram. So if we want to calculate the moment at A, so if we get a line like this, so this will be the shear force at A, this value, or V, sorry. So this will be the shear value at A, and this will be the moment value at A. So if I ask you, what is the shear value at A? What is the moment at A from the drawing? So from this drawing, VA is equal to 6.857 kilonewton. This is clearly given to us or clearly for us. What is MA? MA is this coordinate. So if we get it by percentages from this two triangle, so this distance is 2 meters, this distance is 3 meters. We want to MA, so we will compare it to 20.57. So MA will be 20 over 3 times 20.57 kilonewton meter. So MA is 2 over 3 times 20.57. So the moment is 13.71 kilonewton meter. Okay. Do you have any problem with these two values? So this is shear at A, moment at A. This is what we need from the beam. So the beam was given to us. So what we need from the beam, from this beam, is to find the values for MA and VA. Okay, so this is first part of the beam of the problem. So now we know that V at A equal to 6.57 kilonewton. Six point 857 kilonewton, and MA is 13.71 kilonewton meter. This is the cross section. (200 millimeter times 300 millimeter). Okay, and again, this is our beam. (12 kilonewton), and this is the element you are looking at, point A, at or located at 75 millimeter from bottom and 2 meters from support B here. And this is the dimension. So this 3 meter, 4 meter. So what is our next step? Our next step is to find what is sigma x and sigma y and tau xy r. Okay. To find sigma x or sigma y or tau xy, we need some properties of the material. So our first step in this part is find cross section properties, which is Ix and A. So how to find Ix or A? This is very simple rectangular section. So A will be first, where is the cross section? Centroid. The centroid of this cross section will be exactly in the middle because it is symmetric. So this 150, 150. This 100, 100. So what is A? A will be 200 times 300, which is 60,000 millimeter square. Ix will be BH cubed over 12, so it will be 12 times 300 to the power 3 over 12, which is equal to 200, 300 to the power 3 over 12, which is 45 times 10 to the power 7 millimeter to the power 4. So this is A and this is I. What is the next step is? Sorry guys, the connection was dropped. Thank you, Dokle. Where you missed my connection? Do you know? Okay. So can you see my screen now? Okay. So the next step is to find what is sigma x, what is sigma y, and what is tau xy. Okay. I'm back now. Sorry, the connection was dropped. So how to find sigma x, sigma y, and tau xy. Okay. For this example, the moment we have here, so this is our moment. So if this is our cross section, x, y. So this is our moment because this was our moment drawing. So this was our bending moment diagram, and it was 20.5 20.57 kilonewton meter. And as we mentioned before, the moment is positive or below the datum. So the tension side, this will be the bottom fiber will be under tension and the top fiber under compression. So all this, sorry. So all this part under tension, the green part, and this purple part under compression. Okay. And if this is a moment, so this moment is mx or my, because it rotates about x-axis, so this is mx. So we have mx in this problem, so we have only sigma x. So we need to find the value of sigma x, and sigma y value will be 0. Okay, because we don't have my value. So my value is 0. So sigma y is 0. So this is okay. So we need only to find sigma x. Okay. So if we look at this cross section again. So this is y axis, this is x axis. This is point A. Somewhere here. Where is point A? Point A is 75 millimeter from bottom was given to us. And if this our cross section was totally 300 millimeter. So this 150 millimeter, 150 millimeter. So point A is somewhere here in the middle between x-axis and the bottom fibers. So as we mentioned, this was the moment at A. So the moment at A was, if we go back, if we go up, so this is the moment at A. It is 13.71 kilonewton meter. So how can we find the stress at A? So sigma x at A will be mx times y over ix. We have got ix here. So we will add ix here. So sigma x at A will be mx. How much mx here? 13.71 times 10 to the power 6 times y over ix. How much ix? Again, ix is 45 times 10 to the power 7. How much y? This is the important thing here. So how much y? Y is the distance from the centroid CG to the point we are studying. So this is y, YA. So this is YA will be 75 millimeter as well. So if we add YA as 75 millimeter, so sigma x at A equal to 13.71 E6 times 75 over 45 E7. This is 2.285 megapascal. This stress is positive or tension? So positive because it is tensile stress. Why is this tensile stress? Because point A in this example located in the bottom half, which is under tension. So we got sigma x. What is the next step? The next step is tau x y at A. So what is the formula for tau, if you remember? V times Q, so VA times QA over IX times T at A. So if this our cross section again, this is centroid, this X, this is Y, and okay, Jacob, no worries. See you later. Okay, so if we have, this is our example. So this is our shear force QA. Oh, sorry, QA was reversed. Okay, and this is our point A. Our point A at 75 millimeter here. So how to find the shear stress? Tau here. Do you know how to find the shear stress? Okay, if we go back here, so if we apply here the formula, we know I, we know V. How much T? T is the thickness at the cross section. So, or the width, sorry, at the cross section. So this is T. So T is equal to 200 millimeter because this is 200 millimeter. So now tau xy at A is equal to V. Oh, sorry, this is V. Okay. So V, which is, if we go up, this is V. So V is 6.857 times 10 to the power 3 to convert it to Newton. times Q. I will leave it now. Ix was 45 times 10 to the power 7 times T, which is 200 millimeters. So what only we need to calculate Q at A. How much Q at A? Q at A, if we look here, so Q at A is the moment of area of this part or the other part. So we can calculate the solid part, this part, or from the other side. So Q at A will be equal to, and to remind you, QA is the first moment of area. Q at A is equal to this area, which is 75 times 200 times the distance from the centroid of this area to the centroid of the whole cross section. So how much is this distance? This distance will be 75 plus 75 over 2, because this part only is 75. This part is 75 over 2. So it will be 75 plus 75 over 2 is 112.5. So this give us, this is 112.5 millimeter. So this give us QA of 1687500 millimeter to the power 3. And please remember, in the exam, you should add the units, otherwise you will lose some marks. Okay, if we substitute again here, so 16,87500. So our final answer for tau xy at A is Q times 6.857 to the power times 10 to the power 3 plus 6.87500 times 6.857 E3 over 45 E7 over 200. So this will give us tau of 0.128 megapascal. Okay. So after all of this, we finally got tau xy here and sigma xy here, and sigma y here is 0. So sigma y equal to 0, sigma x equal to positive 2.285 MPa, tau xy is 0.18 megapascal. Okay, what is the next step, guys? Anyone can help me to know what is the next step is? The next step or the final step is to find sigma 1, 2, which is equal to sigma x plus sigma y all over 2 plus or minus root sigma x minus sigma y over 2 all squared plus tau xy. So what we will do is just substitution. So sigma 1, 2 is equal to 2 point here, 2.285 plus 0.128 all over 2 plus 2.285 plus 0.128 all over 2 plus or minus root 2.285 plus 0 or sorry, minus 0. Minus 0 over 2 all squared plus 1. Oh, sorry, this one. Thank you. Thank you, Wang. Okay, sorry, this is 0. No one. Are you all sleeping? This also 0. This sigma y is 0. So here tau xy is 0.128 squared. So we will have sigma 1, 2 equal to 2.285 over 2, 1.1425 plus or minus 2.285 over 2 all squared plus 128 squared root 1.1496. So sigma 1, 2 sigma 1 will be 1.1425 plus 1.1496. So it will be 2.29 positive MBA. Sigma 2 will be positive 1425 minus 1.1496. Will be almost 0, negative 0.007 MBA. So this is the final answer. Sigma 1 and sigma 2. Okay. Do you have any question in this example? Just check the answers. Hopefully we get it correctly. Just save this picture. Okay, the answers are correct. If you have a look here, so this is our sigma x. This is our tau xy. And this is the two values, 2.2129 MBA and negative 7.2 kBA. Because kBA is very small compared to MBA. So this is similar answer to what we have got here. I have closed this file. So anyway, the answers are correct and we have got the answer correctly. And this is the answer. So I think it will be available on the Link Online website. Okay. And that's it for today. Do you have any problem, guys? I will stop sharing.